Hello CIO world, and welcome to another installment of Chemical Engineering Design. This is heat exchangers. In this lecture we will cover the classifications of heat exchangers, the definitions or rather the effects of fouling on heat transfer, and also how to make use of the overall heat transfer coefficient to simplify the analysis of heat transfer. We will also look at the energy balance across heat exchangers and consider two approaches that are typically used in the theoretical design of heat exchange equipment. Now, the equipment is generally designed by companies that specialize in heat transfer equipment, and a lot of the IP, the intellectual property, is kept in-house. But what we will learn here is the fundamentals of how heat exchangers are typically designed. So namely, the log mean temperature difference method or the number of transfer units method is what is typically used, and the number of transfer units method also is called the effectiveness NTU method because we use two variables, namely effectiveness or NTU to do these exchange designs instead. Now, there exists a wide range of heat exchangers with many principal types of heat exchangers in use today in the chemical process and aligned industries that are tailored specifically for the application. Double pipe heat exchangers are the simplest type, used both for heating and cooling, as are plate and frame heat exchangers. Shell and tube heat exchangers enjoy use in all types of applications, including boiling and condensing, and are even used as chemical reactors to do reactive distillation sometimes, or just typical reactions that A going to B. There are also plate fin exchangers. Obviously, we've learned about fins and we know why we would want to place fins on some exchange equipment. There are spiral heat exchangers. It's got to do with the geometry, how these heat exchangers are actually built in terms of the fluids flowing past each other. Right, and then also air-cooled heat exchangers, which is like an air conditioner or a radiator of a vehicle that are typically used in coolers and condensers. And then also direct contact heat exchangers for quenching and cooling applications, like what we do with our pyrolysis unit in the Department of Chemical Engineering, where we pass a cold fluid through some vapor that is coming into the condensing area, and there's a direct contact between the vapor and the cooling fluid because the vapor becomes part of the cooling fluid. And then also we have things like aggregate vessels and fired heat exchangers as well. The double pipe heat exchanger is both cheap to construct and simple in its manufacture and design, with fittings and tubings readily available off the shelf, and these are typically what you would build if you have a microbrewery at home. Now, they are very useful when small heat transfer areas are required. Okay, so like my domestic home microbrewery, I don't need a lot of heat exchange, and the temperature differences aren't that big that I'm working with. Because of their tubular design, they can withstand huge pressures too, because piping is very easy to design for high pressure applications. Unlike other types of exchangers, like the shell and tube or the plate and frame, because these are going to be very expensive if you're going to design them for high pressure applications, where the high pressure is on the shell side for the shell and tube heat exchanger, and also for the plates. Plates are not a very good geometry for withstanding high pressures, but we'll get into that just now. The problem with double pipe heat exchange is obviously the lack of surface area that's created, and the more complex heat exchangers obviously make up for this. The double pipe heat exchangers can be modified quite easily. They can be cleaned, maintained very easily, and have also low pressure drops compared to other types of exchange equipment. Now, although heat exchangers such as the double pipe heat exchanger is less efficient and less compact, um, it also will require very large lengths of pipe to compete with other exchangers. So it should always be remembered that this type of heat exchanger nonetheless does have an application. It has its place in heat exchange, and you can use it irrespective of the disadvantages. And the disadvantages are simply there to remind you of the considerations and how to decide on whether you should pick this one or whether it's a bad idea. Now, the shell and tube heat exchanger obviously uses tubes. It is by far the most commonly used type of heat exchange piece of equipment that you'll find. So if you are in industry ever and not a FMB, then you can go to any part of the process and you are typically going to run into a shell and tube heat exchanger. The configuration of piping achieves a larger surface area than just a double pipe heat exchanger, with a small volume of space utilized because you can stack the pipes, and the pipes are then set in place by what are known as baffles, and the baffles then help for fluid flow through the shell side. It also has a very good mechanical layout. These have been designed for many moons, many years, decades, etc. And so they have a well-established fabrication technique or set of techniques. It can be constructed using a wide range of materials, obviously. Material of selection is very important for chemical engineering design. Even if you're just doing heat exchange design, you must remember to pay attention to materials of construction. And these exchangers can be easily cleaned. Specifically the tube side. The shell side can be a bit tricky. I saw when I was at Sasol how they had opened a shell and tube heat exchanger to clean it, and it can be quite a procedure to clean the shell side. But the tube side, typically you would want to keep your more corrosive or the fluid that will foul more on the tube side, because those are easier to clean. Okay, it's usually less expensive than a plate and frame heat exchanger, but plate and frame heat exchangers can also be automated for their cleaning operation, where you set the frames onto like a chain or something, and then the chain pulls open the heat exchange equipment, and you have automated hoses that wash down the heat exchanger, and then it closes it again. So it can be automated, but obviously this is going to come at an expense. So that being said, there are other types of heat exchangers that are even more compact, with larger the thing is that shell and tubes, in terms of their size, they can be quite big. A plate and frame does really take up much less space. So if you are limited with space, obviously you're not going to go with this. A plate and frame heat exchanger is one of the most compact heat exchangers that is going to be available. So we are doing all of these exercises for internal and external flow over flat plates and all of that. Well, this is where it comes into play in the design of these heat exchangers. The heat transfer coefficients, which you should now know how to determine for flat plates, are generally higher than for the shell and tube heat exchangers. And the cost of the metal per surface area will also be much less than for the tubing. They most often find applications in the food and beverage industries, as they can be readily taken apart for cleaning and inspection. Usually in my office I have a heat exchanger, a plate and frame heat exchanger that I can bring to class, open it up for you guys, and then you can see it. I usually also bring it to CLB, 3 to 1, so you guys can see what a plate and frame heat exchanger looks like. They can also be modified quite easily because of this, because the frame tends to be much longer than the space that the plates take up when they are stacked and pressed together. So you can add more plates if need be, and add more gaskets as well. Even so, plate and frame heat exchangers are much more expensive than all the other options that will be available to you, even though a wide range of plate materials can be used, such as stainless steel, copper. Typically titanium is used because of its strength, and you need to pick a material. Stainless steel is not very good as a material because the thermal conductivity is not that great. A pure metal like titanium will be much better. The plate design is not a good shape to resist pressure, especially differential pressures. On one side of the plate will be one fluid, on the other side of the plate will be another fluid. If there's any pressure difference between these two fluids, it can buckle the plate. And obviously the maximum operating pressure is limited to about 30 bar, where a pipe can go up to 500 bar. Okay. Because of the requirement of gaskets for plate and frame heat exchangers, temperatures are also limited to about 250 degrees Celsius. You do get gaskets that can withstand much higher temperatures of 500, 700, the ones that we use in our pyrolysis applications. You can have a graphite lined gasket, but obviously you're going to pay a lot of money for these gaskets. Also, the pressures of the two working fluids, like I've said, should be matched closely, because you want to avoid buckling at all costs, where one fluid might collapse the confinement space of the other fluid and jeopardize the mechanical integrity of the unit, so you won't have very good heat transfer. So how does one go about selecting the type of heat exchanger? Overall, first off, you should consider the application. How much heat is being required to be transferred? If heat transfer requirements aren't very large, they go with, then go with the cheapest and the simplest option, such as a double pipe heat exchanger. Also consider the cost and benefits, as well as the operating conditions, the temperatures, the pressures. If high pressures and temperatures are expected, or fluids will undergo a phase change, then a shell and tube heat exchanger would probably be the preferable choice over a plate and frame heat exchanger, for example. Now, regardless of all of these factors, all heat exchangers work on the same principle. They use the temperature gradients that exist between the fluids that are moving around, to drive the heat transfer. Okay, the three main configurations that exist are namely the co-current flow profile, which is here shown on the left hand side, the counter-current flow, which is shown on the right hand side, and then cross flow, where the flows are going perpendicular to each other, which we will discuss shortly. Now, counter-current is obviously going to be the preferred configuration for obvious reasons, in that heat transfer is the highest per fluid compared to the co-current transfer. So for example, say you have a cold fluid coming in at 25 degrees Celsius that needs to be heated by a hot fluid which is at 100 degrees Celsius. It is possible to heat the cold fluid from 25 degrees Celsius up to 95 degrees or 97 degrees Celsius, while the hot fluid is able to be cooled down right down to 30 degrees or 27 degrees. But note that it is impossible to achieve perfect heat transfer. Okay, and that means that I will not be able, in this example, to cool down the hot fluid to the same temperature as the cold fluid's inlet temperature. Okay, it's just thermodynamically impossible. There will always be some temperature difference between the endpoints, and if you've done the heat exchange well enough, the temperature difference will tend to be in the order of 7 degrees Celsius. Okay, so that's a really good, between 10 degrees. 5 degrees is really, really pushing it. If you go any more, then I think your heat exchange design is probably very wasteful. It's going to be massive. Okay, now why then would you want to use co-current heat transfer? In some applications, this is very necessary, such as with a flooded evaporator that uses a very large temperature gradient at the inlet side to drive the boiling process more easily in the beginning. And then when the fluids start coming out, you control boiling much easier using the co-current option. And this is used in industry a lot of the time. So co-current has its uses, so don't rule it off completely, but countercurrent is obviously by far most useful for us in most of the applications. Cross-flow heat transfer differs from the first two mentioned configurations in that the two fluids flow perpendicularly past each other. Heat exchangers based on this configuration can utilize the benefits of conduction, obviously, and convection for heat transfer, much in the same way as shell and tube and plane and frame can, but they also have a more open design to them, whereas the other two, the shell and tube and plate heat exchangers, are closed, completely closed. The two fluids are completely confined, whereas these can be open designs, and as such they are typically used for things like a refrigeration system. Like, look at your refrigerator at the back, you have a heat exchanger at the back. Air conditioners, automotive radiators, and just keep in mind that the external flow can also be mixed, or it can be unmixed by using baffles to separate flow, as shown on the right hand side. Now, the design of heat exchangers goes hand in hand with their application and how transfer is optimized by such designs. In the design of a shell and tube heat exchanger, for example, flow enters and leaves the piping through what are known as headers, and the pipe midsections are supported by baffles. The baffles have a second usefulness in that they help to guide the shell side fluid over the pipes in a cross-flow type manner, as shown in the top left diagram. It is also important to determine the flow in terms of which flow goes on the shell side and which one goes on the tube side. So the criteria to consider are the flow temperatures, the operating pressures, viscosities, as well as flow rates, and what are you doing with the heat exchange in the first place? What are you trying to achieve? The configuration here is shown in the horizontal layout, where the shell and tube is lying down. You can also design the shell and tube to be sitting upright, similar to what is done in nuclear reactors, where those are different designs. It looks a bit different, but it is a form of heat exchange design. Alright, now let's move on and discuss heat exchange and the equation. So heat exchange needs to exchange heat efficiently, of course. Heat exchangers need to exchange energy very efficiently. And how do we go about this? We consider certain aspects like the area, etc. Now the primary coefficient, because we are working with moving fluids used for this purpose, considers the resistance to flow, which would obviously now become more familiar for you guys, because we've been doing a lot of flow through pipes and things like that as well. Now recall that the resistances are made up of the convective heat transfer coefficients of the two fluids, as well as the thermal conductivity through the tube wall. Now the summation of these yield what is referred to as the overall heat transfer coefficient, and is specific to the current application and equipment in question, but the overall heat transfer coefficient is also defined per fluid. It can be defined for the entire system, but in fact there should be more than one coefficient per transfer area, taking into account things like fouling, etc. Now, every heat transfer equipment has two surface areas that it deals with: A, I, and AO. So A inner and A outer. Even plate and frames, obviously, it's the same surface area. So only for, okay, let's talk shell and tube, only when we have a wall thickness that is small enough and the thermal conductivity of the tube material is high enough, as in the case of using copper or aluminium, we can then equate these two coefficients and adopt a universal overall heat transfer coefficient. And this is typically done because the approximation that you end up with is still very much reasonable to give you a good design for heat exchange equipment. Now, for quick estimates, there are of course ranges of these coefficients that are known in industry that can be used and that can be sourced from literature depending on which industry you are in. If you're doing liquid-liquid, vapor-liquid, vapor condensing, gas-liquid, gas-gas, etc., all depends on the fluids in question. Now, another useful reason why we wish to define an overall heat transfer coefficient is that we can include it with the fouling. Okay, so we can incorporate fouling factors into the overall heat transfer coefficient. Now, fouling factors will occur most definitely whether you like it or not, and therefore you should always consider taking this into account. Just remember, do not assume fouling won't occur. You are lying to yourself. So for water streams, for example, pure water, processed water, not only will the salts that are present dissolved in the water precipitate out of the pipes, you could also end up with algae growth, biofilms, scaling, poop, whatever, you name it, sand. There is sand even in the drinking water that's coming out of your tap. There's a little filter on the tap that usually picks up all the sand particles, but there's sand sitting in your geyser. Your geyser's filling up with sand as you watch this video. So whatever the fluid, fouling is most likely to occur in some form or other. So just accept it and deal with it by adding it into your calculation. However, fortunately, we have at our disposal some typical fouling resistances available to us in the literature, and these are incorporated into the calculations using the form of equation that is shown below. Of course, you can calculate this using an experiment, and you can do this at work. If you are sitting at work one day as an engineer and you need to just find out why your heat exchanger is not working, you can actually determine the overall heat exchange coefficient, which is something that you actually should have been doing in CLB 321 this year. If you had access to the labs, we would get you guys to determine these things. So the question is, you guys have your assignments. How do you go about designing a heat exchanger? What if your boss suggests we use an available heat exchanger instead of getting a brand new one designed for us off the shelf? How would you determine the performance of such a heat exchanger? Well, there are two methods that are used typically, the log mean temperature difference method and the NTU method. Alright, so the log mean temperature difference method is typically used to design the surface area of heat exchange so that the desired temperature drop that you envision can be achieved. While the NTU method has a very useful application where if you already know a heat transfer area or you have an existing heat transfer equipment and you want to know how it will perform, it can predict things like the temperature drop. Okay, so certain applications will not necessarily have temperature drops per se. Consider boiling, consider condensing, and note that only the latent heat is transferred to the fluid undergoing phase changes. So as the fluid enters and leaves, it is at the same temperature. Some other considerations are to design the heat exchange equipment as you expect them to operate. Just remember, heat exchange equipment is generally designed at steady state operations. You will definitely not want to operate at unsteady state. Okay, it is very unusual and uneconomic to operate under unsteady state conditions in industry, and that is why we have been hampering on the point to teach you guys steady state design applications. Now also, although you should assume that the outer surface is perfectly insulated for heat exchange equipment, remember that you have the tools at your disposal, and you will need to specify an insulation material to achieve this assumption. It goes without saying that you should never make empty assumptions you do not intend to fulfill or validate. Okay. Now, if you are asked, or let's say you asked me, what the most important thing to consider when applying the log mean temperature difference method, my answer would be size. Size is important. You want to achieve the most efficient heat transfer possible with the minimal size. So bigger is not always better. And size here is not just referring to heat exchange area, but also the overall sizing of the equipment that goes hand in hand with this. So of course the equipment size will depend on how small you can design the heat transfer area to begin with. Size depends on the genetics of the system, such as the mass flow rates, the quantity of energy being transferred, thermal resistances, the subordinate temperature, the cold temperature or the hot temperature, whatever it be, as well as the surface area. The method for designing heat exchangers is discussed not only in the prescribed textbook that we have, but also in some of the recommended ones as well, such as Coulson and Richardson's Chemical Engineering, Volume 6, which should be available at our library for you guys, and also obviously online. First off, a suitable heat exchanger should be selected. Thereafter, any unknown temperatures that you may have are to be determined, and this is based on your process design, and it is also based on things like if you're using cooling water, a utility, or steam. You will know what temperature the steam or the cooling water is coming in at, and you simply use an energy balance. Q is equal to mCp delta T to determine the last unknown temperature for the outlet of those utilities. Alright, the next thing to do is to determine the log mean temperature difference, and then for non-latent heat applications, where you don't have a phase change, a correlation factor is also determined using temperature ratios. We'll get into that just now, as well as the overall heat transfer coefficient. And lastly, the area of heat transfer is determined. Now typically we would want to design a shell and tube heat exchanger with very thin walls, but if you're working with high pressures, don't do it. Just design safely at least. Just keep in mind that the log mean temperature difference only applies to co- and countercurrent heat exchange applications. So if you don't have these sorts of flow configurations, then you would just generally determine a normal delta T in that regard. The correlation factor F is necessary as it takes into account physical things, physical limitations for the exchange equipment, so such as the type of flow configuration, its geometry, how is it designed, the operating temperatures, as well as the tube and shell configurations. As I said before, shell and tube heat exchangers, because of their standard established usefulness in industry, they will have very good correlations available to assist in their accurate design. Okay. To determine the correlation factor, the inlet and outlet temperatures are used to calculate the temperature ratios of P and R. Now, for boiling and condensing applications, the correlation factor is always taken as 1. And remember this because I'm going to try to trick you in an upcoming semester test. The correlation factor can be found graphically as shown here. Okay. And R is located as various trend lines, and on the in the green shading we have P, which is the other temperature ratio, and it is read off on the x-axis, and where these 2 points intercept is where we can find a point to determine the correlation factor F. Also pay attention to the fact that there are different types of configurations possible, and so there are different graphs that apply. So for example, this graph is for a 2 shell pass and a multiple tube pass of either 4, 8, 12, etc. Any multiple of 4. Okay. And also note that if you're not using a shell and tube heat exchanger, if you're using a cross flow heat exchanger instead, you would want to use a possible alternative graph. And also just keep in mind that cross flows too have different arrangements that must be taken into account. So for this graph, this is for one fluid that is unmixed while the other one is mixed. Now, the alternative method to the LMTD method is the NTU method. This method defines what is termed as an effectiveness of heat transfer, which is a ratio of the actual heat transfer and the maximum heat transfer. The numerator is found easily using a typical energy balance, MCP delta T, while the denominator is found by determining the maximum temperature difference for the entire system. And this temperature difference is used in conjunction with the smallest product of the mass and CP for whatever fluid this applies to. So you consider your 2 fluids, you determine the product of their respective mass flow rates and heat capacities, and whichever product is the smaller, this is the one that is used in this equation. So try to remember that and practice. There are obviously tutorials that you can go over to practice these sorts of calculations. Next, we also define what is known as a dimensionless group. Again, another dimensionless group, and this one is called a net transfer unit, okay, which is a ratio of the overall heat transfer coefficient multiplied by the area over the minimum MCP term, which we have defined before. A capacity ratio is then also defined as shown. We have used this sort of ratio before, apart from the mass flow rate. It's similar to the K, the specific mass ratio. Okay, so similar but not the same. With these 3 terms, they are, let's say, functions of each other. So it is possible to determine heat transfer potential for heat exchanger in question using these 3 terms that have been defined. This method has 2 different approaches. You can either determine the effectiveness term. You would first obviously then need to determine the correct heat exchanger, which, as you can see, requires then knowledge of the NTU as well as the capacity ratio C to be known. Because if you look at these correlations, epsilon is equal to a function of these two other terms. If instead you know the effectiveness, then you would determine the NTU instead, and then that can be used to determine the overall heat transfer coefficient. Or if you know that, you can then determine the transfer area that can be expected, etc. But overall, this method is very useful if you really don't know what to expect from the heat transfer equipment. You don't know what temperatures to expect to get out, etc. Yes, again, it is possible to find these values graphically as with the previous factor F that we were talking about, that correlation factor. Kind of a similar thing. Here we plot the effectiveness against the NTU. The one graph on the left is for parallel flow. Okay, parallel flow, remember, co-current, countercurrent. The one on the right hand side is the case for the countercurrent flow. It is also to be remembered that the shell and tube heat exchanger can have many more different configurations, and so just remember to choose the right or select the correct shell and tube heat exchange configuration that applies, or the cross flow configuration if you're working with that instead. Now notice that these graphs have a trend line that corresponds to the capacity ratio equal to 0. And where do you think this would apply? Obviously, it would apply for cases like phase changes, boiling and condensing for interest's sake. So with that, we end off this lecture. Good luck. Try to complete some of the tutorial questions, and hopefully you will be able to apply this knowledge to heat exchange design, not only in CIO, but also next year if you need to design a heat exchanger for CPJ 421, and hopefully you remember some of these interesting facts and figures for when you are in industry one day. Goodbye for now.